Hi everybody, can you hear me? Yes, you can. So today I'm going to be talking about blocks in Ruby because blocks are one of the constructs in the Ruby programming language that really lends some elegance to the language. And as I'm sure you've noticed, you can do some pretty amazing things with blocks. For example, you can do something like this, where you define a variable, as I did over here, with a string outside the scope of a block, and then you can just use it inside the block. So I ran into a situation in my code recently where this scenario seemed to stop working, and the code looked something like this. So I had up there in the red block a let block that was defining test index. And then inside my it block, I had two nested blocks I was creating. So the first one over here was being created and passed to class eval. And inside that block, I was then creating another block and passing that to a method called model. And it was inside the second nested block that I was using test index as indicated over there. And based on the example that I showed you on the previous slide, I thought this would just work. But when I ran the example, I got this error saying that Ruby didn't know what the local variable or method test index was. So this was strange, and what was even stranger was that when I played around with the code a little bit, I found this slight modification to the code where I created a local variable myIndex inside the it block, assigned test index to that, and then used myIndex inside the nested blocks. Everything just seemed to work just fine. So I came up with a bit of a differential diagnosis to try and understand what was going on here. Theory one was maybe the problem was that they were nested blocks. So I thought maybe you can't define a variable outside the scope of two nested blocks and then use it inside the innermost block. And so to test this theory, I came up with this example. I came up with this example over here, where I defined the string variable and used it inside two nested calls 2 times, and that works just fine, as I'm sure doesn't surprise you. So theory number 2 was maybe the problem was that I was using let over here to define test index. So I did a little bit of digging, and I found the following RSpec documentation that says that let actually defines a memoized helper method and not a variable as I first thought. And so I thought, okay, maybe the problem is that you can't use a method defined outside the scope of a block inside a block. But I quickly came up with this example over here that shows, in general, this seems to work as well. So here you can see, I'm just defining the string method, and I'm using it inside the block just fine. And so my final theory was, okay, maybe the problem was that the code is just corrupt. And there's maybe some problem with RSpec and some bug in the RSpec code that's making my example fail when it should actually be passing. And again, it didn't take me long to come up with a real-world example showing that this seems to work in general just fine as well. And so RSpec being the problem here did not seem likely, and I didn't pursue that route. And so it was at this point that I realized, okay, if I was going to understand what was going on here, I probably needed to understand the underlying mechanisms that make blocks so powerful in Ruby better. And so the first question is, what is a block really? Well, a block is just Ruby's implementation of Sussman and Steele's closure, which they defined as being a combination of 2 things. It consists of a lambda expression, which is just a function that takes a set of arguments. And it also has an environment to be used when calling that function. Now, for blocks, obviously, this environment is going to have to include the entire surrounding scope for my previous examples to be able to work. In the underlying C code for Ruby, the block looks something like this. It's called, it is an object, and it's called RB_block_T, as you see over here. And it's got various properties. It's got an isec pointer, which is a pointer to the underlying lambda expression of the closure. And for those of you interested, it is actually a pointer to a set of YARV instructions to be executed by Ruby's bytecode interpreter. But for the purpose of this talk, you can forget I just said that. Then there's also an environment pointer. Now this is a pointer to the surrounding stack frame of the block. In other words, it points to where the local variables and method, or actually only the local variables of the currently executing method are located. And it's this environment pointer that gives the block access to the variables defined outside the scope of the block, inside the block, as we will see in a minute. Okay, so now Ruby uses this environment pointer over here to do some pretty interesting things on the stack. And to see what I mean, we just need to take a look at what happens on the stack during a normal method call in Ruby. So the method we're going to be looking at is this display strings method, where you'll see it's very simple. It just has local variables string 1 and string 2 defined in it, and it basically just outputs the combination of the two. So if we want to take a look at the stack, or what happens on the stack when we call display strings, you will see that, as expected, a stack frame gets created on the stack. It has space for, and it has slots for local variables string 1 and string 2, and any arguments that you pass to the method when you called it. In this case, there aren't any. Then I've got 3 dots there to indicate there's some other housekeeping work that gets done as well. And then Ruby also creates a special slot for the method call. Now, this SP, by the way, that's just the stack pointer. Now, Ruby uses this special slot over here to track whether you passed a block as an argument to display strings. And it kind of makes sense that this block does get its own slot, because when you call a method with a block, you are basically just passing that block as an argument to the method. Now, what Ruby does, in this case, we're not calling display strings with a block, so the special slot just remains empty. But what Ruby does do is it sets an internal current environment pointer, as I show over here, to point to the special slot of this executing method. Now, this environment pointer is related to the environment pointer I showed you on the previous slide. So this environment pointer in the block is specific to the block, and it gets the value of the current Ruby environment pointer when it gets created, but that value gets saved down and it doesn't change for the block. Obviously, each block can have its own one, and it could be different from the next block, but this one is the block's special one and it doesn't change. This environment pointer here is Ruby's current environment pointer, and it points to the currently executing environment and is going to change as your program executes. Okay, so this is what happens during a normal method call in Ruby. Now let's see what happens on the stack when you call a method with a block. And the method we're going to be looking at is this call to times over here. So I've just put it inside the display strings. I'm showing it in the context of display strings because anything you execute in Ruby is executing in some method. And so it has a surrounding stack frame. So even if you're executing code in the console, it's going to be executing inside the eval method, right? So it's going to have a stack frame. And so anything that happens is always happening in some surrounding stack frame. So this is the method call we're going to be looking at. It takes this block, and you'll see it uses string 1 and string 2, which are the local variables defined inside the display strings method. So here is the stack for the display strings method call again. It's the same as it was before. Ruby's got the environment pointer pointing to the special slot. And now it's busy executing the display strings method. It hits the call to times. This is another method call, and so another stack frame gets created for the times method. It also has a special slot, and because this time we passed a block to the call to times, what Ruby does is it creates the block object on the heap. Now remember, block is an object, and so it goes on the heap because that's where objects go, right? And what Ruby does next is it sets the environment pointer property of that block to the value of Ruby's current environment pointer. And when it's done this, it sets the special slot of the times method to point to this block object. All right? So this is everything that happens during the method call to times with a block. Now times starts executing. And what happens when it executes is it eventually hits the yield statement, which means the block code needs to execute. And all Ruby does when it executes block code is it just creates another stack frame for the block. So here it is with all its spots for local variables, etc. It also has a special slot as usual. And what Ruby does now is it sets its current environment pointer to point to the special slot of that stack frame. Okay, now you'll notice when I did that, I didn't delete the old environment pointer. I actually just renamed it to previous EP. And the reason I did that is because in the background, what Ruby does is it creates a kind of ladder of environment pointers over here that gets used whenever you try and access variables inside the block that were actually defined in the surrounding scope of the block or even in surrounding nested parent scopes. And the way it does that is it basically just starts at this position in the environment pointer ladder, which was the position for your block's environment pointer, and then it moves down the ladder looking for the local variable defined in some outer scope that you are trying to use inside the block. So this is basically what happens this is actually called dynamic variable access, and it's what happens when you try and access these outer variables. Now, there are some other housekeeping things that happen as well that I've actually left out. So there's a lot of work needed, for example, to copy the block's properties, such as its environment pointer, into a slot, into the stack frame. But that really isn't important right now. The point here is that actually the reason that we can see these variables outside the scope of the block, inside the block, is just this environment pointer ladder over here. So that covers variables. Now the next question is, why can we see methods defined outside the scope of a block inside the block? So why does this bit of code here work? It obviously can't be by the same mechanism. Because if it was the same mechanism, then my test index helper method I had in that RSpec example, which I then try to use inside some nested blocks, should have been visible inside the inner block. But we know that didn't work. And to see how this method access works, we need to take a look at the block object again. So here is the Ruby block object with its isecond environment pointers. And turns out that something's missing, and that something is the self property of the block. And this self property gets set to point to whatever object was active when the block was created. In other words, it points to the method owner of the currently executing method, and that's basically the reason you can see the values in the methods of the currently active object outside the block, inside the block. Okay, well, we can see the self property in action in our code actually, if we want to. So what I'm going to do is I'm going to show you quickly how this works. So here I've got a block tester class that I'm creating. And you'll see it's basically only got the one method, and all it does is it just yields to whatever block you pass it. The next thing I'm going to do is I'm just going to look at my class over here that has, in particular, this one method. So you'll see this test method over here in which we create the test object and then call its block method. And the point here is I want to see what self is going to be when I call this block inside this method. I think a gut feeling actually says that it's going to be test object because that's kind of what it looks like. But when we execute our code, when we create an instance of my class, and then actually just execute that method, we'll see that actually what gets returned is actually the instance of my class and not the instance of block tester over here. This is consistent with what I said because in my earlier slide, because this self over here points to the owner of the test method, which is an instance of my class. It's not test object. And if you think about it, it kind of makes sense because you know intuitively you can access method 1 inside this block. And the reason you can access it is because self is set to the instance of my class. Okay, so Now, you think, based on what I just said, that this example of mine, I still think it should have passed, because over here I have test index, which is defined, we know now, as a helper method in RSpec. And you kind of think that RSpec would be smart enough to add that helper method to whatever RSpec object is active inside this it block, which means that the self property of the first block will be set to point to that RSpec object, which means the self property of the second block should be pointing to that RSpec object, which means that test index should be accessible inside this block. But as we know, this doesn't work. And if we take a closer look at this code, we will see that actually this one method call that takes the first block is actually class eval. Now, you might remember this slide from my talk 2 years ago, where I went on and on about how important it is to always keep track of what self is when you are calling class or instance eval. And in particular, I said that self is always going to be set to the class when you call class eval. And so basically what the slide is saying is that class and instance eval are different than normal methods that take blocks, because they set self to be the class or something else, rather than setting self to the currently active object, the outside of the block. So I may as well add a third line to my table and say that for all methods except class or instance eval, self is going to be set to the currently active object. So we take a look at my RSpec example again, and we see that self in the first block will hence be set to the class of Quattro page. That makes it the active object in that block, which means self of the second block will also be set to the class of Quattro page. And I'm guessing that there's absolutely no method called test index on that class. There's also no local variable called test index, and that's why this example failed. Yeah, so a bit embarrassing for me considering my talk 2 years ago. But everything I just said also explains why this example over here worked, where I made a slight modification, as I had, if you remember, a local variable myIndex, which I set test index's value to, and I used myIndex inside the blocks instead of test index. But we know that because of its environment pointer, the inner block has access to the local variable defined outside of its scope, and that's why we could use myIndex inside this nested block. Okay, so that's all I'm going to say about my RSpec example. I think it's time now to move on to another use of blocks in Ruby that really lends some elegance to the language, and that is its use in define method. Now, you may or may not know, in Ruby there are two main ways in which to define instance methods. The first way is, in this first paragraph, to just use the def keyword, and the second way is, as in the second paragraph, to use define method. Now, the difference here is that whereas this second paragraph actually works, the first one does not. And the reason the first one doesn't work is because the def keyword is actually a scope gate in Ruby. And all that means is that once you use the def keyword, you lose access to all the variables defined in the surrounding scope inside this method. And so Ruby is not going to know what string 1 and string 2 is inside here. And so when you try and call the method, it's going to fail. But you'll notice define method actually takes a block. And what it does is it creates this display strings method that it's creating to actually execute the block code every time you call it. And we know that a block has access to these local variables in the surrounding scope via its environment pointer, and that explains why defining display strings in this way actually works. Now, you may ask, well, given its relative elegance, why not just always use define method and forget about the def keyword completely? Well, it turns out that using blocks does not come without its overhead. So if you remember this slide from a little while ago, you'll remember that when we called times with a block, Ruby needed to create the object on the heap, copy the environment pointer into it, set the special slot to point to that block, and then every single time yield was encountered by times, it needed to create an entire new stack frame move the stack pointer when it did that, set the current environment pointer to point to the special slot. It needed to save down the value of the previous environment pointer, and there was all the other housework, such as copying values across from the block to the stack. And this second bit, more or less in this gray block over here, needs to happen every single time that times hits a yield statement. This happens 10 times in our example, but as you know, it can happen hundreds or thousands of times. And so yes, blocks can be quite slow, and it's the use of blocks that makes the method created by a defined method comparatively slow when it runs. Also, it can be quite expensive in terms of its memory use, as we'll see just now when we talk about lambdas. You might ask, how slow are blocks really? Well, we can do a quick test. I hope it works. So here, I've just got some benchmarking code. I've just got a simple while loop that goes around 10,000 times and adds 1 and 1 together. And we see that's the amount of time it takes, which looks a lot different from last week, but anyway. And then now I'm doing exactly the same thing, but I'm just passing a block 2 times instead. And we'll see that it takes a little bit longer. Usually the difference is much bigger. Let's try that again. Yeah, so in general, I found that it takes about 50% more time to do it using a block than to just do a normal while loop in Ruby. And there's some code examples showing that using a block and passing it 2 times can take up to 71% more time than just doing the same thing using a normal while loop in Ruby. So blocks really are quite slow, and if we care about the speed of a Ruby code, which I mean often we don't in Ruby on Rails applications, you're probably going to want to try and avoid the use of blocks as much as possible. Okay, back to the slides. Okay, so now I mentioned lambdas just now. What is a lambda if not just a block as a data value, right? So it's a block you can pass around and do things with, simply. And so if you look at this bit of code here that creates a lambda, that takes a block, I think it's quite obvious that lambdas are also just objects in the underlying C code for Ruby. They look something like this. They are called rb_proc_t. And it has various properties. Not surprisingly, it has a block object inside it with all the usual things. And it also has an isLambda switch, which is set to true when you create a lambda, and it's set to false when you create a proc using the proc keyword. And that seems to be the basic difference or structurally at least, between a proc and a lambda in the underlying C code for Ruby. I was surprised when I saw this. Anyways, besides that, there is also some other properties such as the endVal property, which we will see in action in a minute. Okay, so lambdas are blocks, so they're quite amazing by default. But as this bit of code here shows, they're actually even cooler. Because what we're doing here is this display strings func method, it's got 2 local variables, and then what it does is it defines a lambda, passes a block to the lambda that uses those local variables, and then it returns the lambda as its return value. So over here, the return value is then assigned to this func value variable, and we're executing a call on func value. Now, if you know how stacks work at all, you'll know that the fact that this last line of code actually works is quite impressive. Because if we take a look at what happens on the stack while we call display strings func, we'll see that here's its stack frame with its local variables, string 1 and string 2. Then it gets to the line where it creates the lambda, and it returns this lambda and assigns it on the stack to the func value variable. But you'll notice when I did that, the entire stack frame for display strings func got wiped off the stack. And along with it went the references to the string 1 and string 2 local variables. So now, theoretically, there aren't any more references on the stack to the string 1 and string 2 objects on the heap, which means they should be garbage collected and they can't remain available to your program anymore. And yet, as I said, this line of code here executes just fine, and it will print out the values for those two variables. So how can that be? Well, to see how it can be, we once again need to take a look at what happens on the stack and heap. Firstly, when we create a lambda, and secondly, when we return it. So here is the stack when we are busy executing display strings func. Now it's executing and it gets to the line where it needs to create the lambda. And what Ruby does when it creates a lambda is it actually creates a copy of the entire surrounding stack frame for the lambda and puts that copy on the heap. Now the stack frame isn't naked on the heap. It does have some wrapper objects around it, such as this one. I'm just leaving it off for now for the sake of clarity. So once this copy of the stack frame is created, what happens now is that Ruby creates the lambda object. So here it is. There's its block inside. And it sets its env property to point to the stack frame copy. And the next thing it does is it resets the current environment pointer over here to point to this copy of the stack frame on the heap. So this is an interesting situation because usually this environment pointer points to the stack, but now it's pointing to a location on the heap. Okay, so the lambda's been created. Ruby keeps executing display strings func, and it ends up exiting and returning the lambda. This over here is just showing that the environment pointer property of the block actually gets the value of the reset environment pointer in Ruby. So it's pointing to a location on the heap as well. But as I was saying, the lambda gets returned and now gets assigned to the func value variable. And you'll notice when I did that is display strings func exited and its stack frame got wiped off the stack. But you'll notice what happened now is we have a live reference going from func value on the stack through the lambda object all the way to this copy of the stack frame on the heap. That has references to string 1 and string 2. And that means that because we have a live reference going from the stack to those string objects on the heap, they won't get garbage collected and they can remain available to your program. Now notice this means that lambdas can be quite expensive in terms of their memory use, as somebody mentioned yesterday, because firstly, this copy of the stack frame needs to remain on the heap for as long as the lambda exists in your program. And the second thing is, any objects that you have that have references in the stack frame are going to remain on the heap also for as long as that lambda exists. So you need to watch what you're doing. And obviously, the more lambdas you create, the more expensive it becomes. Ruby does have a kind of optimization around duplication. So if you are creating several lambdas in the same environment, which then uses the same stack frame, Ruby is not going to create several copies of the same stack frame. It's going to make sure they all use the same stack frame copy on the heap. And it does that by checking, does the current environment pointer already point to a location on the heap rather than on the stack? Okay, so there's some optimizations, but clearly using a lambda more expensive than not using a lambda. Anyway, so this is all that happens when you create the lambda. Now all that happens when you execute the lambda is, well, you're executing block code, and we know from our previous slides that that just means a new stack frame is created for the block code, and as before, the environment pointer gets moved to point to the special slot of the block. Now, the longer you look at this diagram, the more I at least start feeling like I've kind of seen it before. But I think the idea here is to remember that when you create a lambda, Ruby creates this copy of the stack frame on the heap. When you execute the lambda, it's this copy of the stack frame that gets used as the environment for this block that executes. I kind of have a theory that that's going to make execution of the block code a bit slow because, as you know, accessing values on the stack is quite a bit faster than accessing the values on the heap, but I'm not 100% sure that Ruby hasn't found a way around this. Something else interesting about this diagram is that you have access to at least one of these kind of wrapper objects around the stack frame. And the way you have access to that is via the binding class. So I can show you a quick small example over here, where I'm basically defining a method. It has 2 local variables inside it. And you can see all I'm doing is I'm returning the binding object out of that method. Now let's see what happens when I call that method. You'll see, yep, I'm getting the binding object back, so that's good. We can go inside this object and take a look around. And you'll see that predictably we have got 2 local variables inside this object called x and y. And now you can do things with this binding object, such as pass it to class eval. So, pass it to the other one, eval. So you can execute this bit of code over here, and you can give it a second argument that is this binding object. And so all you're doing is you're saying to eval, execute this expression please, and use this as the environment to execute it in. And it knows then to go and find this x and y up here where they were defined. You'll notice that there's absolutely no x in my local scope. So you know it's using the x and y that was defined in the method that has now disappeared. If you don't believe me, you can always set x equal to 5 and do the class, just the normal eval again. And again, you see that it's still using the old value. So you can be assured that this environment here is the one it's using. What's interesting about this eval statement is you'll notice it's actually, all it's doing is it's creating a closure, because this first thing over here is just an expression, and the second argument is just an environment to use when you're executing that expression. Okay, so the last thing is that I mentioned lambdas are relevant when talking about define method. So we're looking at this bit of code here now, and it turns out that what define method actually does when it creates the display strings method is this display strings method is actually a lambda. And that lambda uses this block when it executes. And so again, if we take a look at this slide that I had over here, you'll realize that that means executing that resulting display strings method is going to be quite slow, because as you can see, executing a lambda does take quite a lot of work. We can again test this assumption by taking a look at our code. So over here, I'm defining a simple method that adds 1 and 1 together twice. In my first example, I'm using the def keyword. And then I'm redefining almost exactly the same method, but this time I am using the define method to do it instead. So let's compare their speeds when they run. So first I'm running the first method about 10,000 times in a while loop, and then I will switch to executing the second method, which uses the define method instead. And we'll see that, yep, actually, the method we created using the define method that does exactly the same thing runs at about twice as slow. So yes, the define method creates methods that are quite slow. But what using the define method does do is it allows this situation here to work. So you'll see what we have is we have define instance method that has 2 local variables. Then it creates an instance method over here using those local variables, and then it exits. Now again, we've got this problem where the resulting instance method display strings over here is going to be using these local variables that are going to be wiped off the stack as soon as define instance method returns. But we know now define method is smart enough to use a lambda when it creates display strings, which means there's going to be a copy on the heap of the stack frame containing those 2 variables. And that's going to allow display strings to function just fine long after the define instance method over here has exited. And that's a good thing because, as you know, instance methods tend to remain for the duration of your program. Okay, that's more or less all I've got to say today. Here are my details. I'm Code Kitten on Twitter, Jager on GitHub. A lot of the technical explanations I gave came out of this awesome book called Ruby Under a Microscope. And I work for Zappy Store, who's also a sponsor. And we do a lot of metaprogramming and use blocks extensively, if that's your kind of thing. Thanks very much.